Okay guys, so what we're going to have a look at now that we're able to work out number of moles in a solution, and we're able to work out concentration, and as we do dilutions and extractions, we're going to have a look at some actual titration calculations. So the first thing that we're going to look at here is a question from the 2013 C2 paper for the triple award. And we've got a little bit of information here, so the important thing is that we go through that information and we pick out the key and relevant parts that are going to be necessary for us to score full marks on the question as we go through. So let's have a look here. We've got first of all, if we just highlight the important stuff here. So we've got 25 cubic centimeters of M. Oh, excuse me. So the first thing we need to do here, as I said, is highlight the key and important things in the question. So we have 25 cubic centimeters of a MOH. M just stands for metal, so this is a metal hydroxide solution, and it's titrated with hydrochloric acid, and the concentration of that is 0.125 molar. Okay, and we use phenolphthalein indicator. So you're probably going to be asked for the colour change of the indicator at some stage here. So let's have a look. When I read this, what am I thinking? Well, I'm thinking as a teacher, okay, well, MOH means that the metal hydroxide being MOH, hydroxide ions are -1, so this must be +1, which means that my metal has got to be probably, but not definitely, a group 1 metal. So that's the first thing. So in other words, if I get to the end of this question, the likelihood is that my final part of this question is going to be to identify this metal M. So if it's not a group 1 metal, you need to ask yourself some questions and maybe go back and review your answers. Okay, so let's get stuck into this. So first thing is we've got to calculate the average titer. So we have 3 titers here. We have a rough, a first accurate, and a second accurate. Rough titrations do not get included in your average titer. So your average titer is simply these two here, which are both very kindly 14. So we just add those together, okay, and divide them by 2. So it's 14, and we use the same number of dp that they've used up above, but we must put units on this. You might say, well, there are no units here and there are no units here. Well, there may not be, but there are units at the top of the column and the header, so therefore they've covered themselves in terms of units. So there you go, that's the first part of the question done. Next then, if we just dragged over part 2 here, okay, and we'll get rid of that. It asks you for the colour change. Well, if you think about what's going on in here, what you've got is you have your MOH, which is a metal hydroxide, in other words it's an alkali, and to it you're adding the acid from the burette. So phenolphthalein in metal hydroxides are pink. Now as you add acid to it, it will slowly neutralize. So originally it starts off with pink. When it's neutral, it's colorless. Okay, so it'll be colorless at the end. Right, next thing then, what we need to do is get into these questions. So if we have a look at what they're asking us, calculate the mole of hydrochloric acid used in the titration. Okay, so that's pretty straightforward. If you think about the formula, number of moles equals concentration times volume. The concentration is 0.125, and I just abbreviate moles per dm cubed to capital M, multiplied by the volume. Well, the volume of hydrochloric acid used was 14 cubic centimeters, which is 0.014 decimeters cubed. Okay, so 0.125 multiplied by our 0.014 gives me a number of moles at 1.75 times 10 to the -3. Okay, you could write that as 0.00175 if you want. It's purely up to you. Okay, the next thing is that we get the balance symbol equation, and we're going to need that for some of the parts of the question which follow. I should have actually brought your attention to this piece of information here, which told us that originally we took 3.92 of the solid metal hydroxide and dissolved it in 1,000 cubic centimeters of water. in a volumetric flask. So we'll just have a wee look at that, guys, because that will become important as we go through. If you try to sort of visualize what's going on in here, that's a little weighing boat, and within my little weighing boat I have 3.92 grams of my solid being MOH. And I take that and I dissolve that up into a volumetric flask. Okay, so a big volumetric flask which holds, excuse my artwork, which holds 1000 cubic centimeters. Okay, and finally we take out of that, it says here 25 cubic centimeters out of that, so we extract 25 cubic centimeters out of that and put that into our conical flask, so we have 25 cc's there. So let's have a look. If we look at moles as we go along, and this is where the table that we did in the last video is quite important. The moles here, if we say we've got X moles of MOH there, well, how many moles of MOH will we have here? We also have X moles, because whatever moles is in the solid is all put into there. Then we take 25 cubic centimeters out of this. So whatever number of moles I have in here, in the 1000, I will only have X over 40, because 25 cubic centimeters is 1/40 of 1000. Okay, let's look at then just concentration. Okay, well, it's irrelevant there because that's a solid. Let's say the concentration here is C. What would the concentration in here be? Well, it will be exactly the same. It'll be C, because all I'm doing is taking some of this out from here and putting it into there. I'm not adding water or taking water away, so the concentration will remain exactly the same. Okay, so that's fine. Let's get ourselves into the next part of this question, which is part 2. Okay. So the next part is part 4. Okay, so we've got to this time calculate the moles of the MOH. Well, if you remember from down here, we had calculated the moles of the acid. Okay, and the moles of the acid worked out at let me just do it again. So 0.014 at 1.75 times 10 to the minus 3 moles of the acid. Well, if you have that number of moles of acid, you will have exactly the same number of moles of MOH. Okay, so it works out at 1.75 times 10 to the minus 3. Okay, and that's because you have a 1-to-1 ratio there of moles of metal hydroxide to moles of acid. Okay, now, how many moles of MOH then did we have on the 1000? Well, let's go over to what we did here. If that's the moles in the 25 cubic centimeters, which is 1.75 times 10 to the minus 3, well, we will have that times 40 in the original 1000 cubic centimeters. So if you simply take that value and you multiply it by 40, you'll get 0.07 moles of MOH in the 1000 cubic centimeters. Okay, so that's part 5 done. Let's have a look at then part 6. So part 6 says using, okay, we'll just clear this off. So we're using the fact that we had 3.92 grams of MOH dissolved in that original 1000 cubic centimeters to determine the RFM. So we'll go back to using the mass equals number of moles multiplied by the RFM, or in other words, RFM equals mass divided by number of moles. Well, mass is 3.92, number of moles is, we've worked out in the 1000, is 0.07, and if we work that out, that tells me that MOH has got a mass, or an RFM, of 56. Okay, so that's fine, that's part 6 done. Then if we take out part 7 here, we want to determine the relative atomic mass of just the metal M. So if 56 is MOH, well then if we take away the oxygen, which is 16, and we take away the hydrogen, which is 1, that leaves me with 39 equals M. Okay, so the M has an atomic mass of 39. It then asks me to identify M. Well, there I will go to the periodic table and I will look for the mass number of 39, and if I go to group 1, the mass number of 39 is potassium, so M is indeed potassium. And that figures, and that works out fine. I'm not questioning my answer here, because this is, of course, a group 1, and I said earlier in the question that we wouldn't expect the answer of this to be a group 1 metal. Okay guys, I hope that video helps. There are lots of questions on GCSE past papers similar to this, which you may want to go and have a go at. Okay, we're going to have a look then at the next question here, titration question. So this starts off with, to begin with, a little question about an empirical formula which we've got to work out first of all. Okay, so pharmaceutical drugs manufactured and analysed in a specialist chemical lab. Amyl nitrate is a drug commonly used to treat patients with heart disease. It's made up of 72% carbon, 13.2 hydrogens, so on and so forth. So we've got to very quickly just calculate the empirical formula of this, and we'll do that. And, so just a quick reminder on how we do this. So we'll just write our carbon, our hydrogen, our nitrogen, and our oxygen up there. We'll write our masses of each below it: 72 grams, 13.2 grams, 16.8 grams, 38.4 grams. So atomic mass of that is 16, 14, 1, and 12. So our 72 divided by our 12 gives us a nice little round 6. That's obviously 13.2. Okay, that's 1.2, and we have finally a 2.4. So we take the smallest one, we divide it into all of them: 1.2, 1.2, 1.2, 1.2. Okay, so we have, that is 5. Okay, 11, 1, and 2. So our formula is C5, H11, N1. We don't write the 1 in, O2. Very simple. Okay, let's move into the main body of this question and have a look at the titration part. So let's just get rid of that. Alright, so the pharmaceutical drug, okay, is made of a carbon compound. Okay, the formula of that compound is written as X2 carbonate. So what's the first thing that I'm thinking here? Well, immediately I'm thinking that X2 carbonate ions are -2. So if I need 2 X's, that must be a +1. So I'm thinking that's probably a group 1 metal. May not be, it may be just a +1 transition metal compound, but I'm thinking group 1 metal. So we took 3.7 grams of that solid, put it into 1,000 cubic centimeters of deionized water, and it was mixed up thoroughly, and we took 25 of that out to carry out our titration. This time we're using methyl orange. So exactly the same sort of thing as last time. We don't get a results table this time, we're just told that 20 cubic centimeters of 0.125 molar hydrochloric acid was required to reach an endpoint. So let's get stuck into this. Calculate the moles of hydrochloric acid. Well, the volume of hydrochloric acid is 20, so 20 over 1,000 is it converted into Dm cubed, gives me 0.02 Dm cubed. The concentration of it is 0.125. Okay, so the number of moles, therefore, okay, is 2.5 times 10 to the -3. Okay, again, just like the previous one, if you want to write it as 0.0025, that's perfectly okay. So that's B part 1. Let's go and get B part 2 here. Okay, so we've 2.5 times 10 to the -3. Right, so using the balanced equation to determine the number of moles of the metal carbonate in the 25 cc's. Well, that was moles of that was 0.0025, or 2.5 10 to the -3. The ratio here is 2 to 1, so we simply take that number of moles and we divide it by 2, which gives us 0.00125, or 1.25 times 10 to the -3. Okay, now let's have a look then at part 3 here. So from part 3 we've got to calculate the moles of X2 CO3 in 1000. Well, there's the number of moles in this instance here, which was in 25 cubic centimeters. So if we take that and we multiply it by the fraction that is of 1000, which is a 40th, so we multiply it up by 40, that gives me an answer of 0.05 moles of X2CO3 in the original 1000 cubic centimeters. Okay, right. So this question, you'll notice, is really quite similar in many ways to the previous one. Right, so we're up to part 4 and part 5 now. So let's have a look. Using the initial mass of X2CO3, calculate the relative formula mass. Okay, so again we've got to go back to the other equations, which was number of moles is equal to mass multiplied by, divided by the RFM. So the RFM is going to be equal to mass divided by moles, which we've just calculated out as being that. And the original mass of the solid was 3.7. Okay, so if we take 3.7 there, okay, and we divide it by our point, okay, it gives me a mass of 74. So the RFM of that is indeed 74. Then we've got to calculate the atomic mass of X. Well, if we take 74 and we take away the carbon, which is 12, and we take away 3 oxygens, which are 16 each, so 74 minus 12 minus, okay, gives me an answer of 14. So minus, so 74 minus 12 minus 48, 48 is just the 3, okay, gives me an answer of 14, okay. And then our final part of the question is we have to identify what X actually is. Now, a lot of people will go through the periodic table and look for X, look for a metal with the atomic number of 14. The only thing with, mass number of 14, the only thing with mass number of 14 in the periodic table is nitrogen. And some people will actually write that down, even though that's not even a metal. That is in fact the wrong answer, because what we have to remember here is that the 14 is actually X2, 2X. So that is not the atomic mass of X at all. The atomic mass of X is actually 7. Okay, and therefore the identity, if we go to the periodic table, of X is in this instance lithium. Okay, hope that helps. We've got another one or two to follow. So, okay, so we're going to have a look at this question here, guys. So it's about sulfuric acid this time. Okay, so again, you will need to be aware of obviously the formula of sulfuric acid. Okay, and hopefully you all are. So sulfuric acid, we'll just pop it up there. It's 2SO4. So what's going on here? Sulfuric acid used in car batteries. Many garages keep battery acid spill kit on the premises. The acid neutralizer in the battery acid spill kit is anhydrous sodium carbonate. So the mechanic dissolves 3.71 grams of anhydrous sodium carbonate in distilled water, made up to 250. So again, we'll just do our little 3.7. Okay, made up to 250, probably in some sort of volumetric flask. Just right below that, 250. Okay, calculate the number of moles of anhydrous sodium carbonate present in the 250. Well, that's pretty simple. Moles is very simply equal to mass divided by the RFM of it. Okay, and the RFM of sodium carbonate is 106. So you're simply doing here 3.71 divided by 106. Okay, so 3.71 over 106 gives me 0.0 0.35 moles of the sodium carbonate in there. Then calculate the concentration of the sodium carbonate in that solution in moles per decimeter cubed. Well, again, N C times V, so C equals N, which is 0.035 divided by V, which is 250 cubic centimeters, or 0.25 decimeters cubed. So the concentration of the sodium carbonate is 0.14 moles per dm cubed. Okay, moving then on to the main body of this. So titration was carried out to determine the concentration of the sulfuric acid in the battery acid. So 25, so let's again go through and highlight. 25 cubic centimeters of the dilute battery acid, which is sulfuric acid, put into a conical flask, and a few drops of phenethonial indicator was used. Sodium carbonate solution was used, 0.16 mole per dm cubed. Okay, and we needed 31.25 was our average titration of the sodium carbonate solution. So let's see how we go. Name a piece of apparatus used to accurately measure out. Well, that's simply a pipette. What colour change would you observe during it? Well, in this instance, you are taking the sodium carbonate, so your base is Na2CO3 there. You've got your battery acid, oops, sorry about that, your acid in there, so this is colourless and acid, and as you add the sodium carbonate to it, the first drop of excess sodium carbonate is alkali, so it will turn pink. Okay, right, let's have a look at the next part then. So calculate the moles of sodium carbonate used in the titration. Well, that's the mass of sodium carbonate. Okay, that is the concentration of sodium carbonate. Calculate the moles. Moles equals concentration 0.16 multiplied by 0.03125, which is 31.25, divided by 1,000. Okay, gives me number of moles of sodium carbonate used in the titration as 5 times 10 to the minus 3. Again, you can write that as 0.005 if you want. That's purely up to personal preference. Okay, so into the next part of the question then. Right, use the equation. Okay, use the equation for the reaction. Okay, you've got to calculate the moles of sulfuric acid. Well, this is simply a ratio. We have a 1-to-1 ratio. So if the moles of sodium carbonate were 0.005, well, the moles of the acid reacting in the titration is exactly the same. Okay, so that's part 5. Part 6 then says calculate the concentration. Well, we've set up here with 25 cubic centimeters of the acid. We've said here we've got that number of moles. C equals N, so which is 0.005. The volume is 25 cubic centimeters, which is 0.025. So the concentration of the acid works out there at 0.02 moles per decimeter cubed. You would write, but I can just leave it as capital M. Okay, so this is the final example that I'm going to do. So this is one on drain cleaner. Okay, and again we'll go through it and we'll look at the key and relevant points. We've got barium hydroxide as a group 2 metal hydroxide. Okay, using drain cleaners to determine the concentration of it, we took 25 cubic centimeters of the barium hydroxide. Okay, put it in a conical flask, a few drops of phenethonium, and we titrated against hydrochloric acid, concentration 0.2. And there's the all-important equation. So that's pretty much all the information that we need in order to be able to do this question. So let's go across and see what the main information is. Okay, we'll just probably bring that with us. Okay, well, perhaps not. Okay, so question 1 is again calculate the average titer. Now remember, rough titer does not come into average titer, so average titer is those two added together, okay, added together and simply divided by 2. So the average titer is 22.45, and remember there are no mention of units down here, so you need to clearly put the units on. Calculate the moles of hydrochloric acid used. Well, we need to just go back and double check the concentration of the hydrochloric acid. So it was 0.2 moles per decimeter cubed, and we've worked out that our mean titer is 22.45. So it's 0.2 multiplied by 22.45 over 1,000, or 0.02245. That will give us the number of moles of the hydrochloric acid which is used. So that gives us a number of moles of hydrochloric acid used as being 4.48 times 10, to the minus 3 there. So moving on to the next question. So use the balance equation to deduce the number of moles of barium hydroxide that reacted with it. Well, if we go back to the number of moles, or the equation here, we'll see that the number of moles of acid, okay, to the number of moles of the barium hydroxide is a 2-to-1 ratio. So in other words, we will take this value here and we will divide it by 2 to get the number of moles of the barium hydroxide, which gives us the answer of 2.24 times 10 to the minus 3, and that's moles of the barium hydroxide. Okay, calculate the concentration of the barium hydroxide in moles per dm cubed. Well, if we go back to the start of the question, you'll see that that was the number of moles of barium hydroxide, and that was in 25 cubic centimeters of barium hydroxide. So if we remind ourselves of our equation, where C, concentration, equals number of moles divided by volume. Number of moles is 2.24 times 10 to the minus 3. Our volume is 25 cubic centimeters. We need to divide that by 1,000 though to get it into our decimeters cubed, and that gives us a concentration of the barium hydroxide as 0.0896 moles per decimeter cubed. I'll just write capital M there. Okay guys, so that's as much as I'm going to do. I think I've done an introduction video and a video with I think 4 worked examples there. So what you need to do is go away and find a few past paper questions. If I just put this screen up here, there's a list of past paper questions from the CCA exam board, which you can pause the video now and attempt those. The mark schemes are available online, or I have them, one of the two, and I think I have done those 4 there as my worked examples, so you can go back and have a go at the ones in the blue highlight now and check your understanding. Hope that helps.